We're going to continue with Chapter 8. This is the second lecture for October 20th. Last time we began the rules for Lewis structures, and the first rule was to count valence electrons. The second rule was to find the central atom, whether it's by electronegativity or by the unique atom, if you only have carbons and hydrogens, find central atom and single bond, all the others to it. The third rule was to complete the octets, unless it's hydrogen, and then of course it only gets 2, so 1 bond, no lone pairs. The fourth rule, which we looked at last time, if you have more electrons on the structure you drew than on valence electrons that you counted, then you need to remove electrons from the central atom and form multiple bonds. We're going to talk about multiple bonds. We're going to start with a compound called acetylene. It's C2H2. So let's follow our rules. Number 1, count the valence electrons. I'm going to fly through this part because you need to use your periodic table. Each carbon has 4 valence electrons. Each hydrogen has 2. So we have 10 valence electrons. Now we're going to string the carbons together. They're kind of co-central atoms, and we're going to put the hydrogens off them. Now why are we doing that? Well, we're doing that because hydrogens cannot do more than 1 bond. That was rule 1 and rule 2, and now I'm going to complete my octets. So rule 4 is check valence electrons. And rule 5 is also check valence electrons, but we'll come back to rule 5. This is actually sort of like rule 4b. So let's count the valence electrons on the structure I've just drawn. 2, 4, 6, 8, 10, 12, 14. I have way too many valence electrons. So I'm going to take 2 pairs off, 1 off each carbon. Now I have the proper number of valence electrons, but I have unsatisfied carbons. And so I've got to try to get those octets back for carbon. And the way I do this is just like the last slide says, rule 4 says, you make multiple bonds. So this carbon is going to donate its lone pair to form a multiple bond. Okay, so let's check this out. We still have the right number of electrons. This carbon has 2, 4, 6, 8. This carbon's happy, it has an octet, but this carbon only has 6. So I'm going to take this second lone pair and also add it to the electron density in the center. So now if you count these, both carbons have an octet, the hydrogens have a duet. I have the right number of electrons, so I think that's a good Lewis structure. Let's try it again. Nitrogen. Now again, first step is valence electrons, and each nitrogen has 5, so 10 valence electrons again. Putting the nitrogens together, completing their octets. And when we count this, we have 14 electrons, which again is way too many. So I'm going to knock off 2 pairs, 1 off of each nitrogen. Now I have the proper number of electrons, but I have unsatisfied nitrogens. So I'm going to take a pair of electrons from this nitrogen and donate it to the bond. So now I've got nitrogen on this side and nitrogen on this side. And I look at it, and this nitrogen is not satisfied. It doesn't have an octet. So we're going to do it on the other side. And again, we have a triple bond. check it for yourself, but this has, both nitrogens have octets, that's an N. Both nitrogens have octets, and they're the proper number of electrons. The atoms that frequently will form multiple bonds include carbon. You saw that right here. Oxygen, nitrogen, you saw that right here. Sulfur and phosphorus. Rule 1, valence electrons. 4 and 12 is 16. Rule 2, put the unique in the center. Rule 3, complete the octets. Rule 4, count the valence electrons that I've just put into this structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 2 too many. So I have to take those extras off the central atom. But carbon is now seriously not satisfied. So I'm going to leap ahead. I'm going to have each oxygen donate a pair of electrons to their bonds with carbon and form double bonds with the oxygens on each side, with each oxygen having 2 remaining lone pairs. I count my electrons, I count my octets, and this is a good structure. The second problem, CH2O, has 12 valence electrons. Again, the least electronegative except for hydrogen is carbon, so I'm putting carbon in the middle. And I like symmetry, so this is the way I'm lining it up. Completing my octets. And I count 2, 4, 6, 8, 10, 12, 14. Okay, that is too many, so I'm going to eliminate a pair of electrons right there. And now carbon is not satisfied. So again, oxygen is going to donate a pair of electrons to this bonding region, and we end up with carbon double bonded to oxygen, which still has 2 lone pairs, and single bonded to hydrogen. And if you check everything over, we've got the right number of electrons. We've got an octet on both carbon and oxygen, and this is good. Now we're going to go on here. How many valence electrons do we have? 4, 6, and another 6 is 12 again. Now in this case, I have carbon as my central, and it's got 2 hydrogens on it. And then bonded to it is nitrogen, and then nitrogen has a hydrogen on it. So completing my octets and counting the valence electrons on the new structure. 2, 4, 6, 8, 10, 12, 14. Okay, I have 2 too many, so we're in rule 4A again. So I'm going to erase them off my central atom. And now I have an unsatisfied carbon. It does not have an octet, so nitrogen's going to share a pair of electrons again. And we end up with and if you count all the electrons, you'll find that we have the correct number, and we have octets for both carbon and nitrogen. Finally, C3H6. So I have 12, I have 18 valence electrons here. So I'm going to string my carbons together because they're the only ones that can make more than one bond. And I'm going to start at this end with my hydrogens because my chemical formula does not tell me how many hydrogens go on what. So 1, 2, 3, 4, 5, 6. All right, let's go ahead and try that. Completing my octet. And now I count my electrons that are on my structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, I have I don't have any on my central carbon. Okay, that's wrong. Let's try it again. I need to have a lone pair that lone pair on my central atom. So we'll just put one hydrogen on the central atom. And now I know that I have a pair too many of electrons. And so here I am. Oh, and I had a pair there that I forgot about. This pair of electrons gets donated to that bond between carbon 2 and carbon 3, and we end up with this structure, and then we'll see if it's okay. And let's see, so we have the proper number of atoms. We have an octet here, an octet here, an octet here, duets for all of the hydrogens, and 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. That's a good option for that particular structure. So to make this a little faster, we have some basic rules for the atoms. Hydrogen can only form one bond and it can never have lone pairs. Fluorine can form only one bond, but it has 3 lone pairs. Halogens, the other halogens, form one bond and 3 lone pairs if they're not the central. If the halogen is the central atom, then all bets are off. Chalcogens, the oxygen group, forms 2 bonds and 2 lone pairs. Nitrogen and its family forms 3 bonds and 1 lone pair, and carbon and its family 4 bonds, no lone pairs. Wow, that's a lot to memorize. So instead, draw the electron dot notation. Using 1 dot per side, just like Hund's rule, until you have to pair them. Each single electron needs a bond, and the pairs of electrons are lone pairs. So let's try this. Here we have carbon. Carbon has 4 valence electrons, 1, 2, 3, 4. It needs 1, 2, 3, 4 bonds. 4 bonds, no lone pairs. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. There's the lone pair. And these need to be bonds. Hydrogen. Hydrogen has 1 valence electron. It forms 1 bond, no lone pairs anywhere there. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6, 2 lone pairs, just like I said, and 2 bonds. And finally, fluorine has 7, 1, 2, 3, 4, 5, 6, 7. Check out the lone pairs and only 1 bond. I think that's the easier way to remember it. There are exceptions. If you have an atom in period 3 or below, it can form additional bonds. If we take a look at sulfur, sulfur has 6. It looks like it would have 2 bonds and 2 lone pairs. It does want to have 2 lone pairs, but it can form additional bonds. We'll be looking at that soon. So step 6, formal charges. A formal charge is the charge an atom would have if each bonding electron pair in the molecule were shared equally. So for hydrogen, for instance, hydrogen gas forms a bond with itself, and the formal charge would be if hydrogen, each hydrogen, had its own share of the electrons in that bond. The formula we have is the formal charge is valence electrons minus lone pair electrons or non-bonding electrons, either one, plus the number of bonds, or 1/2 the number of bonding electrons. A lot of people learned it differently in high school, so I'm giving you the various options. So again, valence electrons, always the same for a particular element, but the lone pairs of electrons can vary and the number of bonds can vary for that given element. So looking at hydrogen, again, if I were to actually calculate the formal charge for hydrogen, and we're going to say this is hydrogen 1 and hydrogen 2, each one has one valence electron, minus, this is the non-bonding electrons, plus one bond. So 1 minus 1 is 0. And you'll find the same thing is true for the second hydrogen. Here we have chlorine. Chlorine, again, the idea is that this chlorine has this number of electrons, and this chlorine has this number of electrons. So just glancing at that, you'd say 7, 7, that should probably have formal charges of 0. And if you look at it, in fact, 7 valence electrons minus 6 non-bonding, 1, 2, 3, 4, 5, 6, plus 1 bond. There's the bond right there. No formal charge. And obviously the second chlorine is going to be the same. Okay, let's look at something that has different elements in it. And here we have carbon dioxide. Formal charge on oxygen 1. Over here, 6 valence electrons minus 4 non-bonding electrons, this is oxygen 1, and 2 bonds, 1, 2. How about carbon? Carbon has 4 valence electrons. It has no non-bonding electrons, but it does have 1, 2, 3, 4 bonds. So it has a formal charge of 0. The second oxygen is the same as the first, 6 valence electrons minus 4 non-bonding electrons, and 2 bonds are also a formal charge of 0. Cyanide. Well, cyanide is actually a polyatomic ion, and we're going to check its formal charges out. So the formal charge for carbon, 4 valence electrons, minus, it has 2 non-bonding electrons, plus 3 bonds, 1, 2, 3. So 4 minus 5 is -1. Okay. How about nitrogen? The formal charge on the nitrogen. Nitrogen has 5 valence electrons, minus it has 2 non-bonding and 3 bonds. So it has no charge. So the formal charge here is on carbon, and it has a -1 formal charge. Now, when you have a polyatomic ion, the formal charges have to add up to give you the overall charge on the polyatomic ion, which is what I just said. The sum of the formal charges equals the overall charge on the ion. If you have a neutral molecule, and we dealt with several of those on the last page, the formal charges on the neutral molecule must add up to 0. Formal charges can help us to decide which Lewis structure is best. Now here we have 2 options for the Lewis structure for carbon dioxide. In one, we have a symmetrical compound, which carbon has 2 double bonds to oxygens. The second one, we have carbon having a triple bond to one oxygen and a single bond to another. Now, we can determine which is correct experimentally simply by measuring bond length. The shorter the bond, the more bonds it has, the stronger the bond. So this is a very strong bond. It's got 3 bonds. The triple bond is the shortest of the types of bonds. The single bond is the longest, weakest. The triple bond is the shortest and strongest. So if it were this molecule experimentally, we would say it has 1 long weak bond and 1 short strong bond. Whereas this carbon dioxide that I've been drawing has 2 equivalent bonds. But that requires us to actually go into lab and check it out. So sometimes it's easier just to do the formula. So remember, our formal charge is valence electrons minus the non-bonding electrons plus the number of bonds. So for oxygen, oxygen has 6 valence electrons. Both of these oxygens, we already looked at this, have 4 non-bonding and 2 bonds, making a formal charge of 0. The carbon has 4 valence electrons. It has no non-bonding electrons, but it does have 4 bonds. Therefore, its formal charge is 0, and this oxygen is like the first. Now, if we come over here, I'm going to actually do these. Our formal charge on the first oxygen is equal to 6 minus, it has 6 non-bonding electrons and 1 bond. So -1, just like we have here. So I'd put a little -1 up there. The carbon has 4 valence electrons. It still has no non-bonding electrons, and it still has 4 bonds, so it still has a formal charge of 0. Oxygen 2 has, again, a valence electron of 6, minus the non-bonding electrons, it only has 2, plus it has 3 bonds, so we end up with a +1. This is the preferred structure because it has the least formal charges. Both sets of formal charges add up to 0, which is the best, the one that has the least formal charges. So, guidelines. Dominant Lewis structure is generally the one in which the atoms bear the formal charges closest to 0. In other words, you minimize the formal charges. Least number and size of formal charges. Secondly, if you have to have a negative charge, a negative formal charge, it needs to be on the most electronegative atom. Any negative charge needs to be on the most electronegative atom. So looking at these 3 options for our NCO, we can take a look and say, oh, which one's going to be eliminated according to rule number 1? Well, this one. It has formal charges, it has 2 formal charges, and they're larger. These 2 each have the same number of formal charges, so we can't decide about that. But we can decide about which one, using rule number 2, which one is going to be the better structure. You need to break out your electronegativity table here and check to see which of these elements, nitrogen or oxygen, is more electronegative. And you'll find that oxygen's negative or electronegativity is, I believe, 3.4. For nitrogen's is somewhere around 2.9 to 3. I don't remember exactly. So oxygen is more electronegative, and this is the right Lewis structure, or the best Lewis structure. Step 7, resonance. Yeah, we have lots of steps for this. What is resonance about? Well, lots of pictures, and then why? Resonance structures are equivalent Lewis structures that are the same except for where the electrons are placed. You have resonance structures when more than one Lewis structure can be drawn for a particular compound. When that structure contains double or triple bonds, and when experimentally only one bond length exists. The other trick is that when the bond lengths are measured, the bond length experimentally, not only is there only one bond length, but that bond length is shorter than a single bond, but not as short as a double or triple bond. So what we're saying here, this is ozone, and ozone can have two structures. I haven't written in their formal charges. Believe me, there are formal charges. When you look at ozone experimentally, however, it's 1.278 angstroms. Remember, angstrom is times 10 to the minus 10th for each of these bonds. So we do not have a single bond and a double bond. Instead, we draw both equivalent Lewis structures. These are equivalent. They look the same. In fact, they look like you could flip them around until we number the bonds. This is benzene. You've seen benzene before, C6H6. Benzene occurs in a ring structure with alternating double bonds. But who's to say those are where the double bonds are? Perhaps they're here. And when you measure the carbon-carbon bonds in benzene, they're all exactly the same. And this is a model of benzene. We draw our resonance structures, or because benzene is used constantly in organic chemistry, instead of drawing these resonance structures all the time, they draw this guy. And I'm actually going to start with this one because it's a little easier. In fact, I think I'm going to wait this for later. So, valence electrons, 5, 6. I have 18 valence electrons. Nitrogen is my unique, and it's also my least electronegative. Putting it in the center and single bonding the oxygens to it, and then completing the octets. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have too many. So we're going to get rid of one of the electron pairs on nitrogen. Nitrogen is now unsatisfied, so one of the oxygens is going to donate a pair of electrons to the bond. So we end up with which is what we'd expect because we know oxygen wants 2 bonds and 2 lone pairs. Nitrogen wants 3 bonds and 1 lone pair. Oops, this oxygen doesn't follow the rules. So we would do a formal charge check on that. So that's oxygen 1. 6 valence electrons minus 6 non-bonding electrons plus 1 bond. And in fact, this has a -1 formal charge. Well, that's fine because we had a -1 overall charge. But who's to say that that oxygen, oxygen 2, was the one that donated the electrons? It could also be that oxygen 1 did. So in that case, the Lewis structure would look like this. Now these are equivalent. They're exactly the same structure. Remembering this is bond 1, this is bond 2. We're not just turning it in the air. They're exactly equivalent structures. Which one's right? Well, we have to measure the bond length. And when we do, we find that experimentally both nitrogen-oxygen bonds are equivalent. So these are the resonance structures for nitrite here. Exceptions to the octet rule. Now exception 1 and exception 2 we're going to just go through really fast because we're not going to use them in lab or in lecture. These are molecules, polyatomic ions, that have an odd number of electrons. They are free radicals. They have an unpaired electron. Exception number 2, we have a little bit more to say about this. These are molecules, polyatomic ions, in which the atom has fewer than an octet. Beryllium, boron are the most common examples. Boron has 3 valence electrons. Each fluorine has 7. So there's a bond, just like we have here. Boron does that with 2 other fluorines as well. And this is the dominant structure. We have the perfect number of valence electrons. but boron doesn't have a completed octet. Now, other options include double bonding fluorine, which develops formal charges, and fluorine doesn't like to double bond, so these aren't very predominant structures. This one is. Beryllium hydride. Beryllium has 2. Each hydrogen has 1. That's it. And beryllium only has 4 valence electrons. But everything matches, and that's what beryllium does. Exception number 3. Now this is the one we're going to be using. Molecules and polyatomic ions in which an atom has more than an octet of valence electrons. This is the most common exception. Remember, I said this was for period 3 and larger. So atoms on period 3 or larger. PF5. Before I go into that, why is this possible? Remember, period 3, when n equals 3, L can be equal to 0, 1, or 2. We can have S, N, P, and D. So in period 3, you can have some d orbitals coming into play, even though they're not in the valence shell. PF5. Okay, so 5 plus 5 times 7, so we have 40. 40 valence electrons. P. Okay, I'm going to single bond 5 fluorines to it. I'm not an expert illustrator, so those aren't equally spaced, but we'll go with that. Now let's complete the octets. And when we count all our electrons, we do in fact have 40 electrons. But wait, I said that phosphorus, which is part of the nitrogen family, should want 3 bonds and a lone pair. So this must have a formal charge. Let's check it out. If it has a formal charge, then it's probably not going to be the right structure. 5 minus, it doesn't have any lone pairs, and it has 5 bonds. Okay, so it doesn't have a formal charge, but it has 10 valence electrons. That's okay, because phosphorus is in period 3. Again, if the central atom's in the 3rd row and below, it can do this. It can form more than an octet because of the larger size and the d orbitals of the atoms. Sometimes you have to choose between satisfying the octet rule and getting the most favorable formal charges by using more than this octet. And here's a really good illustration. This is phosphate, PO43-. Both of these are good options. In this one, I have more formal charges than this one. This one, just by the way, I have resonance structures for, so let's check that out. All I'm going to do is move that double bond around. We have one resonance structure over there that we already drew. This is the second resonance structure. And this is the third resonance structure. We're just shifting that double bond around. And the final resonance structure. Now again, both, this is the original, okay? When this is measured experimentally, these are all the same length and strength bonds. But so is this. So how are we supposed to determine that? I don't know. It's still up for discussion. All right, so we have a whole bunch of compounds here. Let's get to it. Now, first of all, I already did that one, so we're not going to worry about that. Here we have 26 valence electrons. I'm just going to go down and do my valence electrons. 36 and 22. Those are my valence electrons. I'm going to put the bromine in the middle, single bond the oxygens to it, and complete the octet. Now I take a look at this, and if I do my formal charges, the formal charge on bromine is, well, first of all, let me count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, that has the right number of valence electrons. Doing my formal charge on bromine, I have 7 valence electrons minus 2 that are not bonding and 3 bonds. This is a plus 2. That's not good. Each of these oxygens we've already looked at. This type of oxygen, I call them lollipops. We have 6 valence electrons. They each have 1 bond and 6 non-bonding electrons, so -1. We can form double bonds, and that we're going to do to try to get rid of some of the formal charges. So let's see, I'm going to form a double bond here by taking one of the lone pairs of oxygen and moving it in. I still have 2 lollipop oxygens, and let's check it out now. I still have the same number of electrons. Still got formal charges here. What's my formal charge on my bromine? I know this one hasn't got a this oxygen doesn't have a formal charge anymore because it has 2 bonds and 2 lone pairs. So I don't even need to check it. It has no formal charge. That's a good thing. How about bromine? Because it's changed the number of bonds. So 7 valence electrons minus still only has 2 non-bonding, and now it has 4 bonds. Okay, so it still has a +1. Well, we can probably get rid of that as well by forming another double bond. So we end up with bromine, double bonded to oxygen, double bonded to oxygen, single bonded to a lollipop oxygen, which still has a negative charge. If you do the formal charge on bromine now, you'll find that it has 7 valence electrons as always, 2 non-bonding, and now it has 5 bonds. So its formal charge is gone. So I have reduced the formal charges down to only 1 minus, which I have to have. This is bromate. But I have, let's see, 2, 4, 6, 8, 10, 12 valence electrons, or 12 electrons surrounding this bromine. That's okay. Bromine is a very big atom. Now this, of course, would have resonance structures. You'd shift the double bonds around, and there are a total of 3. So 3 resonance structures. I have 4. I already counted the valence electrons. Iodine is my central atom, so I'm going to attach the fluorines to it and complete my octets. Now I'm going to count my valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. There are only 2 there. 30, 32. Oops. Now, if you look back to Rule 4b, it says when I don't have enough electrons to put them on the central atom. Now I have 36 valence electrons, but iodine has 2, 4, 6, 8, 10, 12 again. That's a lot. Remember, iodine is a halogen, and I said when it's a central atom, it can have something other than the typical for halogens, which is 1 bond and 3 lone pairs. Let's check out the formal charge. It's got to be somewhere here because we have a negative, and each of these fluorines are just exactly what they want to be. So let's just check it out for iodine. 7 valence electrons minus 2, 4 non-bonding plus 1, 2, 3, 4 bonds, negative 1. That's where that formal charge is. Finally, I3 minus. Well, obviously, there's not too much choice about how we do this. And filling in our octets, let's see now. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, 22. And again, if you do the formal charges, you'll find this is the negatively charged atom. So that gives you a good start on Lewis structures. We will continue on next time.